Good morning, Basic Algebra 2 kiddos. We are moving on into Chapter 8, Section 3. We are still looking with exponential functions, and what that means is our exponent is going to be our variable. Remember last week when we graphed exponential functions, you saw that your graph was always a curve. If it was exponential growth, as you went left to right, the graph would curve upwards. If you had exponential decay, that means that the y values were getting smaller. So as you read your graph going left to right, the curve was going downwards. Now today we're going to go ahead and look at how you can use exponential functions to figure out some real world situations. It says in some real life quantities, some of those quantities, they will increase or decrease by a fixed percent each year. And some things are like if you buy a car. When you drive your car, the value actually depreciates, and it could be at a fixed percentage each year. So every year, the value of the car will go down a little bit. Some things maybe go up. Let's say you got lucky and you did like a storage wars thing, and you got a storage unit with like some collector baseball cards. Maybe the value of the collector baseball cards, maybe they increased at a certain percentage every year. So fixed percent every year means that it's going to either increase or decrease the same percentage. The amount y of such a quantity after t years can be modeled by this equation. Okay, so A is what is the value at the beginning. So if you're buying a car, how much did you pay for the car? If you bought a storage unit on Storage Wars and you got baseball cards, what were they worth the day that you got them? Okay, then it's always in parentheses. It's 1 plus the rate if it's growth. It's 1 minus the rate if it's decay. Now, R is the percentage, but you do have to remember that you always have to turn it into a decimal. Okay, so for example, if they tell you 10%, you have to put 0.10. If it is a 5% change, that is 0.05. Remember, to go from a percentage to a decimal, you have to move the decimal place 2 spots to the left, okay? Now again, growth, you add, and think about it. If you're adding to something, you're growing the amount you have. Decay, that means it's depreciating, it is going down, so you are getting less value. In these models, A is the initial amount, R is the percent increase or decrease written in decimal form, T is the number of time periods. So based off of the problem, they might tell you that it's increasing daily or monthly or weekly. So T is just whatever the time period is. It could be months, it could be years, it could be weeks, just whatever the scenario is. And we'll look at that as we go to our examples. The quantity 1 plus R is called the growth factor. And again, if you're adding, it's growing. The value is becoming larger. The quantity 1 minus R is called the decay factor. If you are subtracting, that shows that the value is going down. So we're going to go ahead and do a few examples, and then I will let you go for the day. Okay, so it says write and use exponential models. One year, a clothing company had $1.5 million in sales. In later years, the sales Y in millions of dollars increased. That's important for us to know. If it's increasing, that means we will be adding by 25% each year. So the first couple, I am having us break it down step by step just to make sure that it makes sense. Write an exponential growth model that represents the sales after T years. So at the beginning of the problem, the clothing company had sales of 1.5 million. Now I'm just going to put 1.5, and I just have to make sure that I label my final answer million. Okay, then it's always parentheses, always the number 1. If the value is getting bigger, like it is here, I add your rate. You have to take your percentage and turn it into a decimal. So 0.25 is the same as 25%. It says find the sales after T years. So this is years, and that is my exponent. So this is an exponential growth model that would represent that situation. We just have to make sure that we label in millions, okay? Use your model, so use our function, to predict the sales after after 8 years. What that means is that T is equal to 8. So 1.5, 1 plus 0.25 to the power of 8. Now I'm going to go ahead and enter this in the calculator with you just because I know that's one of the things, is just making sure that you know how to properly enter. So it's 1.5, that represents the value or the amount of sales at the beginning. Open a parenthesis, 1, the value is going up, so it's a plus sign. Your percentage is 25%, which is 0.25, to the power of. Remember, that's really important that you have your exponent. To the power of how many years? We're looking at 8 years. So 8.94, 8.94, and remember, this is in millions. So check that out. That is crazy. If this clothing company is actually continuing to grow at that rate, it started at 1.5 million in sales. 8 years later, they can be expecting to make 8.94 millions. And companies use this type of information so they figure out how many employees can they hire and can they maybe open additional stores because they have the money coming in to fund it. Okay, let's say that maybe they overestimated this and it's not really growing at 25%. Well, what if the sale increase was only 10%? So we can go back, we just have to alter our equation. We are still starting at 1.5 million because that's how much it was at the beginning. It's still growing, okay? So it's a growth, so it's 1 plus, but they're saying, well, what if it was only 10%? Well, 10% as a decimal is 0.10. They want to know, well, if it was 10% instead of 25, what would the difference be? So I'm going to go ahead, enter it into the calculator. So 1.5, 1 plus because it's growing. What if it was 10%, so 0.10 for that 8 years instead of 25? Look at the difference, you guys. This ends up being 3.215, so I'm just going to round it to 3.22 millions. That is a huge difference. So that's why if you are a business owner, let's say you're somebody who at some point you want to open your own business, it's really important to have accurate data before you make your calculations. If you're like, oh, it's growing 25%, if you make predictions, you're saying, hey, I'm going to be making like almost $9 million in 8 years. But if you were wrong and it's really only 10%, you're really only making a little bit over 3, which granted, you guys, this is an amazing amount of money. But this just goes to show you that little difference in your percentage makes a huge difference in your ending result. Okay, let's go ahead and do a couple more just to make sure we've got it. You buy a new computer for $1,500. Okay, so Jeffrey's going off to college and Jeffrey buys a computer, $1,500. The value Y in dollars of the computer, you guys, computers decrease. Once you buy it, if you keep it for a while and then you want to sell it, obviously you have to sell it for less than what you originally purchased it for. So this is going to be a decay problem. The value is going down, and it's going down quite a bit, 40% every year. Write an exponential decay model that represents the value of the computer. So when Jeffrey buys the computer, it's $1,500. It's always, open a parenthesis, always the number 1. It's decreasing, so it's minus. 40% as a decimal is 0.40 to the power of t. And t represents how long is Jeffrey keeping the computer before he goes to sell it. It says use your model. Here's our model. Use your model to estimate the value after 3 years. That means t is 3. So Jeffrey keeps the computer for 3 years. And he's like, all right, I'm going to go ahead and sell it so I can put that money towards a new computer. How much could he make? 1,500, 1 minus 0.40. Jeffrey kept it for 3 years, so that's our exponent. Oh, I'm sorry, Jeffrey. When you go on to Swap and Shop to sell that computer, the value of the computer is all the way down to $324. Granted, you're still getting some money, but it's kind of sad. You spend over $1,000. You guys like $1,500. 3 years later, that's all that it's worth. Kind of crazy. 2 more examples. In January, the average cost of gasoline is $2.50 per gallon. During the year, the average cost in dollars of gasoline increased, so that means it's going to be 1 plus in parentheses, about 1% each month. So T represents months this time instead of years. It's whatever's going on in the scenario. It's time units. It's going up 1% each month. Predict the price of gas in 11 months from now. Okay, so at the beginning of the problem, the average cost of gasoline was $2.50 per gallon. It is increasing, so it's 1 plus. It's increasing at a rate of 1%, which is 0.01. T is the time in months. Okay, so now I can use this $2.50, 1 plus 0.01, predict the gas in 11 months. So I'm going to change T to 11. $2.50, that's the price of gas at the beginning of this problem. The price is going up, so it's a plus sign. 1% is 0.01 to the power of 11 time increments, and we can expect the price of gas to be approximately 2.789, so that would round up to $2.79. Last question. Let's say that you purchase a car and it's $16,000. Well, guys, a car is another thing unless you buy like a collector car. As you keep the car, the value goes down in price, okay? So you purchase your car for $16,000. Every year the value decreases, so that means it's going to be a minus problem. It's decreasing at a rate of 15%. If you decide to sell your car after 7 years, what would the value be? Okay, so how much could you sell it for? You purchased it for $16,000. It's 1. The value is decreasing, meaning going down, so it's minus. 15% as a decimal is 0.15. Every year, you want to sell your car after 7 years, so that's what your exponent is. So let's go ahead and see how much you could sell your car for. Get ready to grab the tissues. This is a sad one. $16,000, 1 minus 0.15. You drive the car for 7 years. You can only sell it for, yes, you looked at that right. You can only sell it for $5,129.23. Welcome to the real world, guys. All right, so that is the beginning of 8.3. Okay, so there is a practice worksheet for you to go ahead and practice some of these skills and concepts on your own. Tomorrow you get to do something called TED Talk Tuesday. Now, TED Talks, I absolutely love, I love TED Talks. You can learn so much. There's a really, really good one. It's called Math is the Hidden Secret to Understanding the World. So tomorrow's kind of a break from actually calculating math, but you get to watch a TED Talk video. A guy named Roger, he kind of talks about all the different ways you can look at math. I think it's super interesting. Make sure you check that out, and I am giving you points just to answer some quick discussion questions for me so I know kind of what you thought of the video, and email those my way, and then we will get back to calculating our own math on Wednesday. I hope you guys are having an awesome week so far, and I'll talk to you soon. Bye.